Well, so now let us start our discussion on circle diagram of induction machine. First, we will draw, you can say this is approximate circle diagram or commonly known as only circle diagram. This now name approx is here because this circle diagram I am going to develop it based on our approximate equivalent circuit. What is approximate equivalent circuit? This is our approximate equivalent circuit. This is here we are giving V1. Here the incoming current is I1, I0, I2 dash, and here we are having R2 dash 1 minus S by S. As I have mentioned, this is representing a fictitious load, fictitious resistance that is proportional to the load applied on our motor shaft. Now, let us quickly write the equation for all this approximate equivalent circuit. What about your I naught? I naught is equal to, we can figure it out like, well, even equation is not required, as I have told you in my last video. We can have open circuit and short circuit, or rather in the context of induction machine it is no load test, and this one is blocked rotor test. So for them we already know the data V naught, I naught, omega naught. Here it is VSC, ISC, omega SC. So you know the magnitude of this, and from this open circuit data you can calculate what is the angle between V naught and I naught by doing this. Now, if that is the case, then let us draw a diagram slightly different than what we do in normal phasor diagram. Normally, we place the voltage or the reference voltage. Here, it is quite apt to consider V naught as our reference voltage because V naught is the normal line voltage, and that is why normal line or phase voltage, whatever you want to consider, that is totally known and constant, so you can consider this as reference voltage. But instead of placing it as a horizontal line, let us place it as a vertical line. This is our V naught. Now after knowing theta naught, here, okay, one thing please note that you have to do all this in a graph paper, right? So better what I can do is that, just a minute. Well, so I have taken this PowerPoint blank screen so I can draw an object, and here I will have a means I can draw object more clearly and like Here first let us draw that V naught, as I have mentioned that, sorry, about this V naught. So this is our V naught. Now we know theta naught. So just let me check whether it's recording or not. Yeah, it's recording. Now we can draw our theta naught, means I naught at an angle theta naught. See, in exam, you have to do it by yourself in graph of paper, or you can means a scaled graph will be provided to you, and you need to do its like you have to uh, do things as per the scaling of that graph. So this is our V naught. Now let us select our current I naught. So I naught is something like, say we know this current that is having our, just a minute. Yeah, so we are having our V and I naught. So this one is what? This one is our I naught, right? Now here another line need to be drawn, that is our line that is parallel to this horizontal axis, and from the tip of I naught we need to draw another line, that is your, let us select a different color, otherwise it will make you confused. Now one thing, if you understand that what is here means what is this side, like if we consider this vertical height of I naught, then just a minute, let me check whether I can write here on this or not. Well, so this is our I naught, this is our V, right? Now what is, and this is what is this side is your theta naught, this is I naught. So what about this side, this projection, this is your I this length is all about I naught cos theta naught. Now if we do V I naught cos theta naught, what does that indicate? That is W naught. So basically, in this way, this gap, that is the gap between these two lines, it is representing our no load losses. Correct? Now, the way we have drawn this circuit here, if you can see the way, yeah, here you can see that it is the total current is I1 is equal to I0 plus I2 dash. Now, from this diagram, we can also measure angle theta AC. That is your WSC, that is cos inverse WSC by VSC into ISC, right? So if that is the case, it gives us theta SC. Now try to understand one thing. Here we will assume that all this V0 and ISC both are at full load level only. It is not that ISC is not what I told you in the time of first time when we discussed block rotor test, that we can adjust the voltage till or increase the voltage till 125% of full load current flows through your so that may gives you an impression that ISC is 125 times of full load current, but here we are considering ISC is equal to just 100% of that full load current, right? So with that you can figure out the angle, this one, theta SC. Now how we can utilize this information? See, here let us again draw another line parallel to this V. Now this line is also parallel to this V, and if we see here this circuit, we can say that this circuit is also a parallel combination of this magnetizing branch and this series branch, right? The way this series branch, what I am trying to mention, this series branch, sorry, this magnetizing branch and your this parallel branch is this one is connected. See, these two are like they are connected parallel. What is parallel? When the end are connected, then it is parallel. So both of them are experiencing V1 across them, and that is also we can see from the current relation I0 plus I2 dash. So therefore we can draw that ISC with respect to this. Now let us draw ISC from this line. What is happening here? Just a minute. So I have drawn our ISC, right? I have drawn ISC here. So with that, this is our ISC and this angle is theta SC. Clearly theta SC, we can expect theta SC is less than theta naught because the magnetizing branch is obviously more reactive than that series branch. Now, how can we draw the circle diagram and what is the genesis of this circle diagram? Clearly, in this case, if we add these 2 points, like if we find out a line that joins these two, then that will give us something. This yellow line will give us our total current I is equal to I naught plus ISC. That is the maximum current that can be drawn, means during your run time when the machine is delivering full load current. Now here you can argue that, sir, full load current, you just said full load current is equal to short circuit current. Yes, I said it, but there is no harm if the machine reach to this extra current. So, but this is what we can consider, that this is the maximum amount of current. This I naught is required. Why? Because the I naught is required to means cater that no load losses. Otherwise, if I naught is not there, no one will be there to cater that no load losses, and this is required. This ISC is the maximum current that can be circulated through our series branch. Do remember, if you want to cross me in my defense, I will always say that this is an approximate equivalence circle diagram based on an approximate equivalent circuit. Anyway, without making it more complicated, let us see that how this will give us the shape of circle. Now, in order to understand how we will get the shape of circle, I would like to request you to please go through my first lecture, second or third lecture on circle diagram when you are at third semester, and we used to share a very good means cordial relation. At that time I taught you circle diagram and there was a good engagement from your end as per that video is concerned. So you can replay that video to recap the concept of circle diagram, and then from that we can easily proceed. Otherwise, I can just quickly tell you what is here doing. Clearly, this is a circuit with constant constant X and variable resistance, right? So what about the diameter of that circuit, means circle we can get? Okay, let me write the equation. It will help you that I2 dash is always what? I2 dash is equal to V1 by root under R1 plus R2 dash by S whole square plus x1 plus x2 dash whole square. Clearly here, due to this S, R2 dash is variable, and what is the if we are trying to represent it, it is representing a circuit like this. Now see that for this one, or here it is V1, this R is this R1 square. So this is the current. So for this circuit, what type of circle diagram do you expect? If you draw, this is your V, then when r is 0, if we can have r is equal to 0, although here the minimum resistance value will be r1 plus r2 dash by s, but still what you can have here is that for r is equal to 0, lagging current I, that is equal to v by x, right? Means magnitude wise, this is v by x, and lagging this one by an angle 90 degree. And if this is for r is equal to 0, and when r is equal to infinite, then what you will have, the current value will become vanishingly small here, but the current at that time when r is equal to infinite, this circuit will start behaving like a resistive circuit. So the current will be in phase with the voltage. So I have explained it in detail. You can see that one, your current locus will form a semicircle with means that radius of that semicircle is this one v by x, and at any point for any value of r we will have current. We can just connect the point for any value of r, we can figure out the current from this circle diagram. Similarly here in our diagram, if we do it, what we will get, we should get a circle. But the question is that how to draw this circle. The circle what I am trying to draw, we can draw it like using a technique, that is we can understand this ISC line. Obviously this ISC line would behave like our chord of that circle. So how to draw it? For the time being, let me just erase this line. Oh God. Right, this ISC will be chord of the line, and what we know that any line that is perpendicular to our chord will always pass through the center of that circle. So let us draw a line that is perpendicular to our ISC. Hopefully this is almost 90 degree, not very sure, but so this point is our, like from this point we will get the radius. The radius will be this much. How much will be our radius? Radius will be this much. So we can draw an arc based on this. Let me draw it, otherwise for ease of this drawing, I just slightly shift ISC. Still, this theta SC is smaller than theta naught. Uh, well, just a minute. Let me just scale this diagram. Yes, now this diagram is scaled, and let me quickly repeat how we did it. This diagram, first we draw V, that is vertical line. Then from this V we measure theta naught. Then we draw I naught. All this drawing was done in scale. Then this gap means a line that is parallel to this horizontal line drawn from the tip of I naught. The gap between this saffron color line was drawn, and the gap what we are having here is representing no load constant, no load losses, because this is what, this is I naught cos theta, and if you multiply I naught cos theta with V, you will get the power. So this representing no load losses. Now you see that we are having, this one was our ISC. Now for this ISC, what we had is that for ISC we figured it out that this I2 dash will always means the tip of I2 dash will always be on this circle. But how to draw this circle? For doing so, what we did is that we draw a perpendicular bisector on this ISC, and this is a perpendicular bisector, and then we figured out the radius of this circle. This is the radius from tip of I naught to tip of this means this intersection point. This is the circle. One thing, due to my drawing, it may seems that the diagram circle dia was already known to you, but it's not. We can have it like this, means any straight line drawn. So this much is our radius, and by taking it we can construct the circle. Now we need to figure out many other important property. One important thing is that here we can understand that what we are having here is this circle, what we are having is this one, that current will always be in this region. It cannot go beneath it. The maximum value of current is this much for normal operation. So this side is, what is the value here? Our value is, here the value is S is equal to 1, right? Here S is equal to 1, and what is the value here? Here the value is S is equal to 0. In between you will get current for normal motoring, and this is a circle on which we will have our input current, right? Now see here, once we construct this circle, then another few things we need to be careful about. That is, I'm going to make two claims, right? Like, if the circle diagram for a machine is given, then we can figure out its its torque profile and everything for a given power. So this circle diagram is complete and it reveals all about your induction machine. Now, how to proceed? See, we have already figured out the portion of constant losses, that is clear, that is in between this saffron line and this yellow line. We figure it out. Now, what is that? Okay, before I proceed, I would like to quickly recall, help you to remember your air gap power equation. So, what is, or rather, power flow equation for this circuit? So, here what you can write is that this portion is responsible for our core loss and constant losses. Oh God. This is our core loss. This portion is for core loss and constant losses. Means we can, just a minute. So this is our power flow diagram. This software Encodo is creating a hell lot of problem. So everything what was there, what I drew, just erased, and I cannot just means it is not possible for me to means somehow recover them. So this is our with our approximate equivalent circuit, this is our power flow diagram. Now see what is happening here. It's that it's like our with this approximate power flow diagram. Here what we can say that this, if we write it stage wise, first we are having input power minus our core loss minus our stator copper loss minus our this gives us what? This gives us our air gap power. And once we get air gap power, then from that air gap power, if we subtract our rotor copper loss, that gives us output power. Now our circle diagram must be drawn in scale to give us the clear indication. So first of all, we have to figure out that two things are very clear from the construction of this diagram, that any line that is vertical any vertical component of current from this diagram gives us a proportional value of power, because that will be in phase with this voltage and will give us the component. And another thing what we knew about this diagram is that this side is our we are having our no load loss. So this area means this is the constant value of loss irrespective of our load condition. Now how we can figure out or different circuit behavior from this. Now see, we need to figure out the air gap power line. Once we can figure out the air gap power, then we can do it, right? So how we can proceed to figure out our air gap power? Air gap power, see, if we observe this relation, what we can figure out that what is the value of output power when your S is equal to 1. Your output power is 0, right? Output power is 0. Now, if that output power is 0, then what was the total power when you allow this much current to flow through your circuit? This component total represent what? This vertical component total represent, because at that time there was no air gap power, and when it was in standstill condition, total air gap power was absorbed by the rotor resistance. In short, for S is equal to 1, your air gap power was is equal to I SC square R2 dash. So if we want to figure out the air gap power line, what we can do is that we can do things like anyway, not able to delete them. Just let me first delete them, otherwise it is creating. Now see, this is our air gap power. Now here one thing is very interesting, that if we consider, it is like uh, now let us draw a line that is a vertical line from this point on this red line. Just a minute, we need to draw a line on this. So here this is the vertical line. Now let us divide this line in ratio of R2 by R1. So if we divide this line in this ratio, it may cut it somewhere here. Then we need to join that one, like from this line so this is our air gap line. I have used the same color you can see here that here also this is our air gap power. So inside this is rotor copper loss and this is stator copper loss. Now what we can also draw the dividing line based on this, like our this line is our line that is representing rotor loss, or what we can say that this line is basically our output line. Now this is our air gap line, or also you can say this is our, as we know that air gap power is proportional to our torque in synchronous watt, so we can say air gap line is also is equal to torque line. And this one that we are having, this torque line, what just a minute, which, so sorry, I just got disconnected due to some of my system problem. So here what we were discussing about the circle diagram, that now it is clear that anything that is any component of current that is parallel to this v axis represent active power. So now if I claim that I means this particle scale can be considered as power scale also, because this particle scale represent a component of current that is proportional to this voltage, so you can figure out power scale also. And if you are still not clear, then the easiest way to do this scaling is that for your V and I naught, the way you have drawn, that clearly gives this is our W naught. So you know your W naught is you should get it from your no load test data. Then you can suitably scale this vertical side for power scale also. Now suppose I am looking for value of power in terms of vertical scale, that is 2 unit. Like this vertical scale represent power, so I am looking for some value of power that is equal to this 2 unit. Now if I want this amount of power from our machine, then I must know that what is the value of slip at which the machine can supply that power, what is the corresponding value of torque, what is the corresponding value of efficiency, everything we can figure it out from this circle diagram. Now if I am looking for this 2 unit power, what we need to do is that from this S is equal to 1, we have to draw a line that is exactly 2 unit line. So this is my requirement of power for which I want to know the corresponding value of slip. Now what is this? This is output line, and like when your machine speed transits from S is equal to 1 to S is equal to 0 here, at any point on this circle, this vertical distance gives you the corresponding value of power. This vertical distance gives you the corresponding value of power for any value of slip. So if I am looking for this 2 unit power, what I should do is that I should draw a line. I am trying to use same color as that was used for our there in that diagram. So now clearly this line is parallel to our power line, and one thing now to our one we can observe a very surprising things that at this particular point, oh god, at this particular point we are getting 2 points for this slip, like for two different value of slip, say s2 and s1, we are getting same amount of power from our machine. Now we have to determine that at which value of sleep the machine will operate. It is impossible for the machine to machine cannot operate at two different speed. It must operate for a corresponding value of power. It must operate at a single value of speed. So how we can figure out the answer? In order to figure out the answer, we need to go back to our torque slip characteristics diagram. So what is that torque slip characteristics diagram? Here, okay, so let me go back to that point where we started. Yes, this was a typical torque slip characteristics curve. Now you can see that here, say 60% of maximum torque, although this is for torque, but for power also we can draw similar kind of curve, and you can see that we are getting, say if we specify this in terms of torque requirement also, we are having, say this is our S1, this is our S2. Now if my machine torque requirement is 60% of maximum torque, then which point my machine will operate, whether it will operate at S1 or S2. Now irrespective of any machine, now I am going to tell you something that is true for any machine, whether it's irrespective of machine construction and that means its nature, if I draw the or the torque speed characteristics curve in any point, say this side is your speed and this side is your torque, the point where you are having your like this torque speed curve slope is negative, that is the stable operating point. Like if we have this kind of, so you will find here and here at both the point, at this point and at this point, both the point you can have equal amount of torque you can get from your machine, but the point where your torque slip torque speed characteristics is negative, that point namely dt d omega slope is less than 0, that point indicates a stable point. And the reason is quite obvious, because torque into speed gives us power. So if we want stable system, that means the power should not go out of bound, and therefore any means in steady state power is constant, so any deviation from steady state in terms of torque, if torque increases, the speed should decrease to make sure the power remains constant. But if you consider, if torque increases, then the speed is also increasing. Now more torque means more acceleration means more. So basically your machine cannot operate here for a given torque requirement with the slightest perturbation, even if you artificially start here, with the slightest perturbation, machine will reach here. Either it will come here or it will stall. So from this analysis, what we can see there, that between this S1 and S2, well, so one thing we need to figure out, that the region which it is our, in this diagram, the region that is having from 0 to SMT, this region we are having the torque slip curve is having negative slope. For all this curve, this region means S is equal to 0 to SMT. This is our stable operating region. This is our stable operating region. So, although from this point, another important observation we can make is that although rotor resistance is not desirable and it's harmful in terms of efficiency and machine heating, but for a high value of rotor means resistance, what we can see is that it helps us to extend that stable operation region. So you can have basically a wider speed control. Like you can see that in this region, say these two are very extreme, but as long as your R2 is as large as 0.5x2, you are having slip value is equal to, that is almost 0.5. So 0.5 slip is not a matter of joke. That means you can utilize this whole, means I am talking about this curve, so you can utilize this entire segment. But see, if your R2 is small, then what you are getting? You are getting a slip value is, means your stable operating region is only limited between a speed value for which slip is below 0.1. It is, let us consider this point is 0.1. So you are not getting wider speed variation for stable operation. So this is very important, and with that we can figure out which one is stable. Is that your this S1 point, oh god, S1 is stable S1 is our stable operating point, right, and S2 is an unstable point. So however, one thing we need to know is that what is SMT? SMT is that point for which we can expect maximum value of torque. Okay. So where we can get that maximum value of torque? Obviously, maximum value of torque will be the point from which the vertical distance on this torque line will be maximum. That maximum torque point is a point for which the vertical distance of this is maximum, right? So how can we figure out this point? Using our knowledge in geometry, any line that makes an angle drawn from the center and makes an angle that is 90 degree to our torque line is this point is giving us our slip SMT, right? This angle is 90 degree. This angle is 90 degree. This is a SMT. So this is our stable operating zone and this side is our unstable operating region. So basically what you will get is that you will get your stable operating region in this area. Now, can you tell me what is the physical interpretation of this point where a perpendicular drawn on output line intersects? Any idea that this point is basically our SMP, the slip at which. Okay, now so this is S1. Now just let us conclude that at S1 what is our output power? Just draw a line parallel to V. Actually output power we know because output power requirement was already means mentioned to us. So this is our output power, output mechanical power. Now for that, what is the input power? Input power is that our input power is these blue lines indicate input power. This total thing. This length is our input power. Now what about our efficiency? Efficiency will be from this point. Let me select another color, otherwise you will get confused. Efficiency will be, this is our total power and this side, this much is output power. So you just measure these two lengths and find out its ratio, you will get efficiency. What is the value of torque? Torque value is your line till this pink line. This will give you the value of torque in synchronous watt. Obviously you need to divide this synchronous watt by your speed to figure out the torque in Newton meter. Well, now what is the value of current? It is very easy to figure out. The value of current is, just join this S1 with your this is the value of current, and this I naught always remain constant, and this is your I2 dash for that given load. So I hope this makes sense to you. Now for your quick revision, that how we started with the with our input such as V I naught, and uh, we had our inputs V and I naught. So with that V and I naught, we draw this red or maroon, whatever it's this line. Now on this line, now what we did is that again from this tip of I naught we draw a line that is parallel to V. From this line we draw theta is C, and this was ISC. Do remember, once you select a scale for I naught, suppose I naught is equal to 5 ampere, and you select 2 unit to represent 5 ampere, then means you can select scale for voltage and current, then power scale will automatically be means fixed, and this angle is theta naught. So either you can select the scale for V and I, or V and W, or W and I. Meaning you cannot select V, I and W, all the three scale independently. Now once you select scale for I naught, you get the magnitude of this blue arrow. Then from the tip of I naught you draw ISC. Now on that ISC you draw a perpendicular bisector shown by this white dashed line. Now that perpendicular bisector cut this line at point say C. Now you take this length C to here, say it is point O. This OC gives you the radius of your power circle. Then you draw this complete circle. Now once you draw it, then from this point you draw a perpendicular on this line, and then you divide this perpendicular line in ratio of R2 by R1. The bottom part should represent R1, the top part should represent R2. You get a point, you join it with O, you get this as your torque line, and this is your output line. Now for a given power requirement, you draw a vertical line that is parallel to these two lines here. Now from the tip of that vertical line you draw a line parallel to your output line. Let that line cut your torque slip characteristics, your circle at 2 points. Now the point which is in between S is equal to 0 to S is equal to SMT is in this cyan color region. You should consider that point, and the other point, this must be discarded because this represents an unstable point. Now once you figure out the point at which your system is operating, you can measure the output power. Output power, obviously you know it, and you will get the same length. This is your output power. If you draw from that point, if you draw it here, you will get your input power. If you find out the ratio, that will give you the efficiency. Then well, one thing that we should discuss, suppose if I give you like a power value, means and your say what another thing. Suppose you one like one operating point, how to figure out the sleep, like how we can see that the value of sleep is that here what is this is our rotor power loss for a particular value of current. So if we obtain the at any point the sleep value is this is what this vertical length, this is your above torque line, it is air gap power now, and this much is the corresponding rotor loss. So what we know that air gap power at any slip is equal to what rotor copper loss at that slip by that slip value. So if you do this ratio, like so if a properly scaled diagram is given, suppose if I give you this diagram as machine circle diagram and ask you to find out slip at a particular point, say the way we determined that 2 unit, and based on that 2 unit we find out the but how can we figure out the what is the value of slip? Obviously this slip is less than SMT, it falls within 0 to SMT region, but how to figure out the value of slip at this operating point? The answer lies, you have to draw a line perpendicular on your torque line. For that line you need to measure the you have to figure out the ratio of length of this red line and this blue line, you will get the corresponding value of slip. So that is all about your normal circuit diagram based on your approximate analysis. We will discuss that exact circle diagram in our next video.